Hey guys, welcome to Pre-Calc, lesson 8A.6, solving exponential equations. Before we get to the equations, I want to do a warm-up here. This is pretty typical of what you can expect to see on the calculator inactive portion of our upcoming exam, working with exponent properties to go back and forth from radical form to exponential form. In the first group here, I want you to write each in radical form. So a couple things to remember. This exponent only goes to the x, not the 2. So the first thing you might want to do is just bring down the 2. Next, in a rational exponent, remember, the bottom is the root, which is what goes outside the radical, and the top is the power. So to write that, it's pretty simple. It's going to be the 8th root of x cubed. All right, it doesn't say simplify, so we'll just leave that in radical form like it is. Next one, I've got negative 4x to the negative 5/4. So we have a couple things going on. We have a negative exponent, and we also have that rational exponent again. This negative 4 is not affected by the exponent, so I'll just start by writing that down. Since this is negative, it'll move this to the denominator, or it'll take the reciprocal of that base. It's going to be the 4th root of x to the 5th power. So there is radical form of that exponential expression. Next, we've got 3/4 times x to the negative 2/5. So again, negative and rational. This will move to the denominator. That's already a fraction, so we'll have 3 in the numerator, and the denominator of 4, and then we'll have the 5th root of x squared. So once you get the hang of these properties, these really go quickly. This next group, we are going to write in exponential form. So I know it doesn't specifically say this in the directions, but I want you to rewrite this term here without a radical and without a fraction. So first thing to realize, this 4 is not part of the radical whatsoever, so we'll bring that down. And here's usually how I handle these. I know I have 3 variables, so I'll just start by writing x, y, z. All 3 are underneath this radical. So that will be in the denominator of every exponent. So something over 5, something over 5, something over 5. And then these powers obviously would go in the numerator. So the x will be 3 over 5 for its exponent. The y will be 2 over 5. Now, because the z is in the denominator, that means it's got to have a negative exponent. All right, so that'd be negative 1. All right, my next one. If I don't want to write this as a fraction, I see there's a 5 down here. I would just have to start that with the coefficient of 1/5. I've got an x, I've got a y, and I've got a z. So the y is not part of the radical, so it will not have a fractional exponent, but it's in the denominator, so its exponent would be negative. So it'd be y to the negative 2. The x and the z will have a denominator of 3 in their exponents, and then the numerator for the x will be 6, and for the z will be 1. Now I can simplify this right here, so I'll take a second to do that. That would be x squared, y to the negative 2, and z to the 1/3. All right, so let's move on to solving equations. When possible. Well, first of all, you don't have to write this down, but here's the simple concept. Solve this equation for x. 2 to the x equals 2 to the 7th. Since these bases are the same, I think it's pretty easy to see that x would equal 7 in that case. So our goal, when possible, is to get like bases. Once you get those bases to be the same, you set exponents equal to each other, and then solve. So this is why it's very important that we know our power families. First example here, I have 3 to the x plus 2 equals 9 to the x. Well, right now, I can't determine anything about those. They're not equal for sure because these bases are not the same. So To get like bases, you always have to go to a smaller base. I know we're conditioned to solve equations with multiplication and addition and things like that, but you're always trying to rewrite the term with a smaller base. So 3 and 9 are both in the 3 power family. That means I'll just leave this as 3 to the x plus 2. But the 9 I have to rewrite. I have to rewrite this as 3 to some power. Well, this one's pretty simple. It's 3 squared, so I'll just replace the 9 with 3 squared. Note, this and that are exactly the same. I didn't change this equation whatsoever. Now, I just need to apply my properties of exponents, take a power to a power. So my equation becomes 3 to the x plus 2 equals 3 to the 2x. And now, you can set those exponents equal. So x plus 2 equals 2x, subtract x from both sides, x equals 2. And it's really simple to check. If x equals 2, I'll plug it in here and here. Well, 2 plus 2 is 4. 3 to the 4th is 81. Plug the 2 in here. 9 squared, that's 81. So 81 equals 81, check. Okay, number 2. I'm looking at the bases. I see a 4 here. I see a 16 there. You have two options, really. You could go 2. They're both in the 2 power family. But I think 4 might be a little bit easier because I don't have to change this whatsoever. So the left side will stay 4 to the 3x. Now, this side, the right side, has to be 4 to some power. Well, let's think about it. It's in the denominator. That means I have a negative exponent. And 4 squared is 16, so that's going to be negative 2. Pretty straightforward once again. Once you have those bases the same, 3x equals negative 2, divide by 3, x equals negative 2/3. Before I move on, let's see. Let's plug it in here. Well, 3 times negative 2/3, let's see, 3's cancel, so that's just a negative 2. And we said 4 to the negative 2 is 1 over 16. So that one checks. All right, let's move on. Example 1, very straightforward. You can fast forward this if you want. Base is already the same, so I just take 2x minus 1, set it equal to x plus 3. Subtract x over here, add 1, x equals 4. I'm not even going to check that one. Let's move on to example 2. So now, the issue here, I have the same base, but I have 2 of them over here and just 1. Now that concept we talked about like this only works when I have a single base on both sides. So somehow I need to put these two together. It's not too difficult. You just have to remember your properties of exponents. When you multiply bases, you add the exponents. So that would be 5 to the 2x plus 4 equals 5 to the 5th. Now we just set those equal. 2x plus 4 equals 5, 2x equals 1, x equals 1/2. Well, again, I'm not going to move on until I check it. It doesn't take that long. Plug a 1/2 up here. 2 times 1/2 is 1. 5 to the 1st times 5 to the 4th equals 5 to the 5th. Now, I have no idea what 5 to the 5th is, but you don't need to. As long as you get this side to be 5 to the 5th, it checks with that. So we're good. Example 3. All right, so once again, I need to get this side to have a single base. That's going to be 4. We just have to remember our properties of exponents when we divide bases. You subtract the exponent. So that's x squared minus 2x equals 4 cubed. Now we can just set those exponents equal. All right, so that gives me x squared minus 2x equals 3. Subtract a 3. Now let's go through this quickly. Factor. And I get two values of x. X equals 3 and x equals negative 1. Now they both should work, but let's check. What if x is 3? 3 squared is 9. 2 times 3 is 6. So I have a 9 here and a 6 there. If I subtract those, 9 minus 6, that would give me 4 cubed, which is what I have there. So I know that one works. Plug in a negative 1. Negative 1 squared is positive 1. 2 times negative 1 is negative 2. So I have 1 here, I have a negative 2 there. 1 minus a negative 2, that's 3. So that one works as well. All right, example 4, I have an 81x squared, 81 to the x on one side, and I have 3 squared to the x plus 1. Again, here we've got choices. We could use 3 as a power family, but because I see this 3 squared, and that's 9, and 81 is in the 9 power family also, I'm going to rewrite that. 9 to the x plus 1, which means over here I need something to the x that has a base of 9. Well, that's obviously going to be 9 squared. Then you just have to multiply those exponents. So that gets me 9 to the 2x equals 9 to the x plus 1. Now we can set the exponents equal. 2x equals x plus 1, x equals 1. Easy to check. Plug a 1 in there. Well, that's 81. Plug a 1 in here. That's squared. That's 9 squared. That's 81. That works. Okay, example 5. 2 and 8. The base is going to be 2. This will stay 2 to the x minus 1 equals something squared. 8 is 2 cubed. That's what we really need to know, those power families, and know them without a calculator. So multiply those two exponents. That gets you 2 to the, wrong color, sorry. 2 to the x minus 1 equals 2 to the 6th. Now set those equal. X minus 1 equals 6. X equals 7. Again, easy to check. 7 in here. That's 6. 2 to the 6, if you count it out on your fingers, 64, which is 8 squared. So that one works. Okay, well, this one here, a little bit more challenging because now I need to work with both sides. All the other equations have been pretty simple because one of the sides was the base. But now, 9 and 27. 27 is not any power of 9, any integer power anyway. So what I need to do is find a smaller base. How about 3? So this would be 3 squared. That's the 9. And I still have this x plus 1. 27 would be 3 cubed to the x. So again, I know I'm going a little bit quickly. Here's the concept. This 9 has to be rewritten as 3 to some power. So you guys understand that this expression and this expression are exactly the same. On the right side, 27 has to be written as 3 to some power, so that this expression and this expression are exactly the same. So now I'm going to multiply here, but don't forget to distribute, and I'll multiply there. So that's 3 to the 2x plus 2 equals 3 to the 3x. And that's the hard part. Once you're here, obviously, this is pretty simple. 2x plus 2 equals 3x. Subtract 2 from both sides. X equals, I think I did that, 2. Got it. So now, let's check. So if I made a careless error there in my subtraction or division or whatever, this wouldn't check, but let's make sure it does. I don't really know what 27 squared is. That might not help me. But then bring a 2 up here. That's going to be 9 cubed. So let's say, I could do that in the calculator, and I know that that works, obviously. But let's say this is the exam, it's calculator inactive, and you don't know what 27 squared is, and you don't know what 9 cubed is. If you're pretty confident you did this step correctly, well, you could plug it in here. That's going to give you a 3. So I have 3 squared cubed, which is 3 to the 6th. I'll plug the 2 in here. I have 3 cubed squared, also 3 to the 6th. So even though I can't really do this in my head, you could check this, and even though it's not a true check because you did some algebra to get here, it's better than nothing. All right, our last one on this page. I've got 1/3 to the x minus 1 equals 9. So I'm guessing here my base is going to be 3. Well, I'll take care of the easy stuff first. That's 3 squared. So over here, I'll have some power of 3 to the x minus 1. The question is, 3 to what power is 1/3? Well, that's going to be a negative 1. 3 to the negative 1. We'll give you that reciprocal. Okay, so now distribute that negative 1. This is 3 to the negative x plus 1 equals 3 squared. And now you can just set those exponents equal. So negative x plus 1 equals 2. Subtract 1, you got negative x equals 1, so x equals negative 1. Let's check. Throw it in up here. Negative 1 minus 1 is negative 2, and 1/3 to the negative 2. You take the reciprocal, so it becomes 3 squared, and 3 squared equals 9. Good. All right, last two examples will be review, but something we want to emphasize this unit. Compound interest. It's a formula that we need to know, and we need to know how to convert that to an annual percent increase. All right, so in this problem, if you invest $2,000 at 3%, what is the maximum amount you will have after 3 years? So that's interesting, maximum amount. It doesn't say how many times to compound it. On the day, I believe it was 4 notes, we talked about maximum amount means continuous. Compounded continuously. So we're going to be using that PERT formula. All right, so the end amount equals our initial amount, 2,000, times e to the r, which is 0.03, 3%, times t, number of years, and it says 3 years. Okay, so you'll throw that into your calculator, and mine says $2,180.35. So that's a very straightforward problem. I mean, this, yeah, you have to understand maximum is continuous, minimum would be compounded annually. But here's where it gets a little bit more challenging. It says, what is the annual percent increase? So what I want you to remember for that, anytime you need to find percent increase or decrease, you have to make your exponential model appear in this form, ab to the x, where this variable exponent is isolated. So what we're going to do with our model here is we need to get our b term. Here's our a term. This is our b term. Because remember, that's your t or your x. So I just need to do that. Not too hard. A equals 2,000 times e to the 0.03 to the t. All right, so what's that? 2,000 and e to the 0.03. Let's see what I get for that. 1.030454. So percent increase is not this. This is your growth factor. It's how far this is from 100%. So what we do now is we take that number, subtract 1, that gives our 0.030454, and then convert it to a percent. So to convert it to a percent, move this decimal over 2 places, goes right there, and round to the nearest hundredth. So that looks like it's going to be 3.05. 3.05% increase. So this right here is the higher level problem. We're going to be attaching this to all of our straightforward, just plug in the year and evaluate the interest. One more, last one. If you invest $5,000 at 4% compounded monthly, so that's our n equals 12 scenario, what is it worth after 10 years? All right, well, that's pretty straightforward. A equals 5,000, you need to know your compound interest formula, times 1 plus the interest rate, 0.04 in this case, divided by however many times it's compounded. So we just said monthly would be 12. All of that to the 12, and remember, these two numbers are always the same. The number of times you compound in a year, then you have to multiply the number of years by that because you're compounding that many times more. Okay, and our years here is 10. All right, that's just straightforward. Plug into the calculator. Let's see what I got. $7,454.16. Okay, now the hard part. The annual rate of return. Now, this is also worded a little bit differently than the one up above. Notice the one up above, it says percent increase. And we see that word percent. I do not see percent anywhere here. It just says rate. So regardless, I still need to get it into that model we had up above. A, B to the T. So in this case, the B term is going to be all of this with the 12 exponent. All right, so let me calculate that. 5,000, and then I'll just leave that as t. So 1 plus 0.04 divided by 12 to the 12th is 1.040742. Now again, because it just says rate, basically it's another way of saying, well, what is the common ratio? What are you going to multiply your investment by every year to calculate its end amount? It would just be this to nearest thousandth. All right, so that will be your annual rate of return, 1.041. Okay, guys, that concludes day 6. Thanks for watching. As usual, if you have any questions, don't hesitate to reach out. We'll see you in class soon.